Okay, so today we'll start to talk about measurable functions. So before we start, we need to introduce the concept of extended real numbers. So the idea is to just include the negative infinity, positive infinity into the set of real numbers, and we call this new set the extended real number, the set of extended real numbers. Okay, the purpose of including these two is in case that the function may take infinity, blowing up at some certain points, we can still work on the function, work on the properties of it. Okay, so these two apparently has the property that for any real numbers, you fall between these two. Okay, so when we add these two, this set of extended real numbers is still order set. Okay, second thing is that when you add a real number to by positive infinity, is still positive infinity. You subtract positive infinity from a real number, you get a negative infinity. Or you add a negative infinity to any number, you get negative infinity. So this is the purpose. This is what we're trying to say right here. So to see for each one, what I mean here is like the sum of x and positive infinity gives us the positive infinity. Okay, and x minus infinity or negative infinity also becomes positive infinity. Okay, so probably I shouldn't write this in a very compiled way, but the idea is pretty clear. You add, as I said, you add a positive infinity or negative infinity. That should be just dominated by the infinity with the proper sign. Okay. Similarly, for this one, it's the same. You subtract the negative infinity, it's a positive infinity. Okay. And also, if you have positive infinity minus negative infinity, then we're just adding two positive infinity. That's still positive infinity. And similarly, you have a minus negative infinity minus negative infinity, minus negative infinity minus positive infinity, you will get negative infinity. Okay. Also, if you put a sign, you put a positive or negative of the, you put the positive of this, you doesn't change the sign. But if you put negative of this, you change the sign. Okay, and similarly, this is true. And you take the absolute value of positive or negative infinity, you get just positive infinity. Okay, so this is straightforward. The idea is pretty straightforward. The sign of a real number is either 1 if the a real number is positive, or -1 if the real number is negative. This case is really special that we will consider it separately actually. The idea is that if you multiply a positive or negative infinity to a non-zero real number, then it will just change the sign if the real number is negative. If you do not change the sign if the real number is positive, the real number is positive. Okay, so that's about product of a finite number and the infinity. And if you multiply two infinities, then the sign is just depending on their own sign. If they have the same sign, then it's positive infinity. If they have opposite sign, it's negative infinity, like this one. Okay, and also be careful that when we have positive infinity, then we cannot subtract positive infinity. It is not defined. And similarly, when we have a negative infinity, we cannot subtract negative infinity, and that is also not defined. And lastly, this is a kind of customized for this course, which is that if we multiply 0 to positive or negative infinity, we get 0. Okay, for this course. The reason is later on we work on the measure 0 set. We're going to multiply the function value over a measure 0 set. And we consider this as 0 even if the function takes positive or negative infinity at that point or over that set. Okay, so this is only for this course. But you know that in general, when we multiply 0 and the positive, 0 and infinity, you should be very careful, since usually it is defined in a limited sense, and it could be any value, right? It could be multiply according to the rate of going to 0 or positive infinity, you could get 0, you could get some fixed finite number, you could get infinity. Okay, so that's a different story. Okay? For this course, you see that this way of definition is appropriate. Okay, so now we're going to introduce the real stuff. We're going to define the measurable functions in this way. So suppose we have a set E. So the E is a measurable set. By measurable set, we mean the one we in the previous chapter. It's a Lebesgue measurable set. Then we say a function defined over this set as a mapping from the set to the extended set of extended real numbers is measurable if for any real number t, this set here is measurable. Okay, so what this set is the set of points whose function value f is bigger than t. In other words, this set is a subset of E and is the inverse image of this interval, right? It's bigger than t, so it's from t to positive infinity. So it's actually the inverse image or pre-image of this interval, and this part is from R and R extended R is R bar. Okay? So if for any t this set is measurable, then we call this function a measurable function, or call the function measurable. Okay, this is a little bit, it's pretty similar to the set of continuous functions. We say the function is continuous if the pre-image or inverse image of an open set is open. Right? This is somehow similar to that. Okay, I'm going to give a remark here. According to our definition, we need to show this set to be measurable for any real number t. But in practice, you can also show that this is true, this is a measurable set for any rational number. Or you can even say that you have a dense subset of R. For example, the set of rational numbers is a dense subset of R. But for any dense subset of R, if you can show that this one is true for any value or any point in the dense set, then you can also claim this function to be measurable. Okay, the reason is if you can show this, if you have a dense set of R and the function this is true for any value in D, then what happens is since it's dense, since D is dense, we can find a sequence for any t. We can find a sequence Rk such that Rk goes down to t, or Rk approaches or converges to t from the right. Right? If like to say this is t, so you have R1, R2, R3, R4 going is approaching to t, because this set D is dense, so you know that this such sequence exists for any t. And you can show this. If you know this, then you can decompose this set into a countable union of this, where we have this f of x bigger than Rk. Okay, if this is true, this is bigger than t means that it is bigger than at least bigger than some Rk, right? Because it's bigger than t means that it's bigger than some Rk. Okay, for k k arbitrarily close to t. So it's just taking the union of that. And if you know this is open, this is the measurable, then the union will be measurable, because the set of measurable set is the Lebesgue measure is a sigma algebra. So taking the union of them is still measurable. Okay? So this tells us that as long as you can show this is true for all the t in the dense set, then this one is measurable for all the t in the dense set, and then you can claim the function is measurable. Okay, so now let's take a few examples. Suppose I have a function f that is mapping from the closed interval to the set of extended real numbers. Suppose it's monotone, then this function must be measurable. Okay, so let's say we consider the case where f is monotonely increasing or monotonely then decreasing. In this case, the function is kind of like increasing, but it could be much more weird than this shape because we just say it's measurable. It could be it could have very strange shape. It doesn't have to be continuous. Okay, so the idea is that we need to check this set. Right? According to the definition, we need to check that if this one is measurable, it's a measurable set for all the t, for all the real number t. Okay, so as you can see, if your t is very large, and all the function and the function value is always less than or equal to t, then what happens is this is t, and everything is below it. Then you can see this set will be just empty because no point can have a function value bigger than t. Okay, and in this case, we just have empty set. It could also happen that your function looks like this, and it cut with the t somewhere. So in this case, if one point has a function value bigger than t, then all the points on the right will have function value bigger than t because the function is non-decreasing or is increasing. So in this case, we actually can easily show that the pre-image or the set here, which is the pre-image of the interval t to infinity, is a part of the interval here from some point to b. Okay, and it could be open, could be closed, but either one of them, these are starting from some point c to b. This is the measurable set. And the extreme case is that if all the points have function value bigger than the t. In this case, that this set is just the whole interval a to b. So you can see that these all are measurable sets, and these are all the possibilities for different values of t. So that's why this function must be measurable. Okay. So next we're going to show several properties of the measurable set. So suppose we have a function f that is mapping from e to the set of extended real numbers, and this e is a measurable set. Okay, so this measurable set is in Rn. Okay, could be in any general n-dimensional Euclidean space, and this e itself is measurable. Then the set below, I'm listing here, these sets will be all measurable sets for any t, for any real number t. Okay, the first one here is just the original definition. This set is measurable. If function f is measurable, then this set is measurable for every t. Okay, this is the original definition. And we can also show that this is a measurable set. The reason is this less than or equal to t is just the complement of this set here, or the e minus this set here. So we know that e is measurable and this set is measurable, so the difference of them is measurable. That's from the previous chapter. Right? The difference of two measurable sets is still measurable. And we can also show that the f of x greater than or equal to t, the set of such points, is measurable. The reason is it's greater than t means that it's greater than or equal to t means that it's greater than t minus any small number, right? Or t minus epsilon. But we can replace epsilon by 1 over k for k being 1 from 1 to infinity. Okay, so it's greater than or equal to t, it's just like bigger than t minus epsilon. But we can replace that by a countable intersection of such kind of sets. And for each one of them, as we showed as we know, it is measurable. So that's why we have intersection of measurable sets, which is still measurable. Okay, and this one, as less than t, means that it's the complement of this one. Right. So if this is measurable, then this must be measurable as well. Okay. Actually, we can instead of using this one as the definition, we can use any of the three here as definition. So if you know any one of these four to be true for all the t's, you can get the other 3. So in practice, you can actually use any one of the first 4 as definition. But for convention, convenience, we just use the first one as the definition. Okay. We can also show that, so from this one, this is not equivalent anymore. But we still know that if this set, it would be a measurable set. The reason is if the points that f of x equals to t, it's just the points that is greater than equal to t and less than equal to t. Okay, so I use a simple notation for this to write this. So this is just a collection of points where the function is less than equal to t. Okay, just write it in short. So you can see this is the intersection of 2 measurable sets. So that is why it's the measurable. This one, for all the points with a value less than positive infinity, it's just just the union of this, right? Just a collection of points. If it's less than infinity, means that it's actually less than some number, and then for k large enough, it will be less than that. It will be less than that. So that's why you can just take the union of the points whose function value is bigger than or equal to k, for k getting larger and larger. And then we know that for each one of this, it is measurable according to this one here. So that's why they take the union of measurable sets is still measurable. And the set of points whose function values is positive infinity, that is just the complement of this, complement of the previous one. Right, so it's just complement of that. The points whose function value is bigger than negative infinity is just the union of f greater than, or f of x greater than equal to negative k. Okay, and similarly, the set of points whose function value is negative infinity is just a complement of the previous one. So this is still measurable. Okay. Now, several simple properties of measurable functions. Suppose we have a function f that is a mapping from the union of 2 measurable sets to the set of extended real numbers. If this function f is measurable on each of them individually, then this f will be also measurable on the union. Okay, the reason is you look at considering the definition, we need to check if this set is measurable for all the t's. But you look at this set is nothing but the union of this set and this set, right? So it's all the points that is bigger than t, so it's either in E1 or E2. I consider them separately and take the union of them, it will be just that. But if function is measurable on E1 and E2, then we know this and this are both measurable. So the union of them is measurable. That's just this. Okay. Next, suppose we have a function from E to R bar, and there's a subset of E which is measurable, called the subset A. Then when we restrict f to A, it means that it's a mapping from A to R, then this will be still measurable. So the key is that if f is measurable on E and A is a measurable subset of E, then f will be also measurable on the subset A. Okay, and the proof is also simple. To show that it's measurable, we just need to check if this one is a measurable set. And as you can see, this means that all the points whose function value is bigger than t, and same time it is in A. So this is a subset of E, and this is also a subset of E, and taking the intersection, it's a subset of E, and both of them are measurable, so that's why this is a measurable set. And that proves that the f is still measurable when we restrict it to a measurable subset. Okay, now let's look at an example. Suppose we have a measurable set E, then the characteristic function of the set E is a measurable function. So recall that the characteristic function of a set E is just a binary valued function. It's equal to 1 if the argument x here is, or the point x here is in E. This will be equal to 0 otherwise, if x is outside. So basically you can think that you have this as the whole Rn, and you have a subset which is E. The function will just take a value 1 inside E and take a value 0 outside. Okay, and this function must be measurable. Again, to show that it is measurable, we can try to see if this set is measurable for all the real value t. Okay, so we can consider several different cases. If t is less than 0, then apparently we have the characteristic function can only take value 1 or 0. So either one is bigger than any negative number t. That's why if t is less than 0, then this set is just the Rn itself, it's just the whole set. While if t is bigger than or equal to 0 but less than 1, in this case you want this two number to be bigger than t, then you can only have the points in E. So that's why this would be equal to E if t is in here. If t is bigger than 1, then we know that there's none of these two can be bigger than some number bigger than or equal to 1, right? So that's why there's no way to find a characteristic for any point. There's no way to find a point such that characteristic function is bigger than the t in this case. So in this case, the set here is just an empty set. So now you can see that for different possible values of t, we can only have these three types of result. And all of them are measurable sets. So that's why this one must be a measurable set for any t. And that proves that this characteristic function is measurable by definition. Okay, now let's consider several more properties about measurable functions. Suppose we have two measurable functions defined on E, and then you multiply a measurable function by any scalar, C, but C is a real number, it is still measurable. You take the sum or difference of two measurable functions, is still measurable. You multiply two measurable functions, it is still measurable. Okay? The product of two measurable functions is still measurable. Okay, the proof is pretty simple. We prove them one by one. For the first one, apparently if c is equal to 0, then there's nothing to prove because it would just make this function 0 function, and that's a measurable function. If c is positive, then we need to check if this set is measurable. So this is the definition, and for this one to be greater than t, you can see if c is greater than 0, then this set is equivalent or is just the same as this set, where we divide c on both sides. Right? We just move c to the right-hand side here, and this is a measurable set because f is measurable. And if c is negative, when we divide c, it will change the sign, but this is still a measurable set. Okay, so in either case, the c times f is still a measurable function. The sum of two functions, the sum of f and g. So if we want to show this is a measurable set, we need to realize that this can be decomposed into the intersection of these two things. So here, f of x plus g of x greater than t is the same as, say, if f of x is bigger than or equal to rk, and you want this g of f plus g greater than t, then the gx has to be greater than or equal to t minus rk. In this case, bigger than. In this case, when you take the sum of these two inequalities, you get f plus g greater than t. But the practice is that it could be bigger than any possible t. So this rt is any real number, right? Just a real number that we labeled indexed by k. And we know there are countably many rational numbers, so that's why we can decompose this into this form. And this includes all the possible cases for this. Okay, so these two are equal. Okay, so if you know the sum of them is measurable, then we can also get the difference of them measurable. The reason is we can just take the f minus g as f plus the negative of g. But we know that from this one, if g is measurable, then negative g is also measurable. So it's the same. So it's sufficient to just to prove this. Okay, for the last one, in order to prove this, let's first look at this set. So suppose f is measurable, then let's say the set of x where fx squared is bigger than t. And apparently if t is less than 0, then this is always true, right? So that's why this is just the e. If t is less than 0, then it's just true, always true. If t is greater than or equal to 0, then this set can be written as the union of this f greater than or equal to t, square root of t, and f of x less than or equal to negative square root of t. Right? Or it should be bigger than, strictly bigger than, strictly less than. But in either case, this is measurable. Okay, so the union will be measurable. Well, if we have this, you can show the square of a measurable function is still measurable. Then we can realize that if f and g are both measurable, then f plus g is measurable. And f plus g squared is also measurable. So this is measurable. And this will be measurable as well. And the difference of two measurable functions will be measurable. And then we scale it or divide it by 4, it will be still measurable. Right? So, but you can see that this is just the f times g. Because when you expand the squares, you see that you got 4 times f times g in the middle. 4 times f and g left. And then you canceled the 4 with this 4 here. And this is how we can show that this is also measurable. Okay, next, this is a bit more another useful result for the measurable sets. So suppose we have a sequence of measurable measurable functions. Fk is a sequence of measurable functions, and then the supremum of the functions, the infimum of the functions, are all measurable. Okay, we'll define this. We'll see more clearly what these two are. And also the upper limit, lower limit of the function is also measurable. They're also measurable. Okay, so let's see prove them one by one. So what this one means? This one is a new function. We call it f, and it's defined in this way in the sense that for every x, fx equals to the supremum of these values. I have f1 of x, f2 of x. They are all real numbers. The supremum of these countably many real numbers is the f of x. So for every x, we can define this, since this is just the numbers. Okay, so now let's see why this f is measurable. This f is measurable means that we need to check if this is a measurable set for any real number t. So these are the points whose function value is bigger than t. And this is the supremum of those fk. So if this is bigger than t, means that at least one of them is bigger than t. Right? At least one of this is bigger than t, or this is bigger than t for some k. And in this case, you can see that you can just rewrite this as the union of this set. And as you can see, this is the measurable set for each k, since fk is measurable. So we're taking union of what the measurable sets is still measurable. Okay? This shows that the supremum of the functions is a measurable function. And similarly, we can do the same thing, or we can use the fact that the infimum of the functions is equal to the negative of the supremum of the negative of these functions. And we know that fk is measurable, so negative fk is also measurable. And the supremum of this is measurable from the previous item. And then you take that another negative is still measurable. So that's how we show that the infimum of fk is a measurable function. And now let's see the supremum, upper limit or lower limit. So let's say that my fk is the upper limit of fk. So recall that the upper limit can be written in this way, where for every fixed k, we can take the supremum of fj over all the j's bigger than or equal to k. Okay, this is another way to write this, and you can see that this one is decreasing in k. The reason is if we have larger k here, we'll be taking the supremum of fewer functions or fewer values, and that is why we potentially will get a smaller value. So this one is so this is a number for each given k, and this number will not increase, will be non-increasing as k goes to infinity. And since it's non-increasing, we know that the limit exists, and this limit is actually the infimum of these points, because you know if you have this is a set of real number, if you know these points are monotone decreasing, then the limit of this is just the infimum of these points, right? So that's why the limit becomes just the infimum. I should say this is a k from. This is just a k from 1 to infinity. Okay. So that's why this is true. And now you can see, since I have a sequence of measurable functions, so the supremum, the supremum of this will be measurable, as we showed in the first item. And then this is a measurable function. We can call it gk if you like. And you know this gk is measurable, and then we take the infimum, it will be still measurable. So that's for the upper limit. And similarly for the lower limit, we can see that the lower limit of the sequence is negative of the upper limit of the negative. Okay, so negative of the upper limit of the negative. So that is still measurable. Okay, so now we actually only proved this first one here using the definition, but the other three are actually, they can just follow easily. Okay, now let's see a corollary. So the corollary says that if we have a sequence of measurable functions, and they convert to some f, then this f is also measurable. So they convert to f in the sense that for each point, this sequence of numbers will convert to f of x. Okay, and then if f is the limit of, it's a pointwise limit of a sequence of measurable functions, then f itself is measurable. And to prove this, we can just realize that this f is just the limit of fk, right? As we proved earlier, as we said earlier. And this limit of fk is just the upper limit, and it's also the lower limit. But we know this is a measurable function according to the theorem above. So that's why this upper limit is just the limit itself, and that's just f, and that means f is measurable. Okay. Next example. Suppose we have a measurable function f. Then we define the positive of f, or f positive, to be the maximum value of f and 0. So what this function actually is this. The f positive of x will be f of x if f of x is positive, it's non-negative. And it will be 0 if f of x is less than 0. Okay. So for example, if I have a function looks like this, then the positive of this function, or the f plus, is this part. Okay, it will be 0 if it's negative, and it will stay the function itself, will be the function itself if it is positive. So that's f plus. F minus is also a non-negative function defined as the maximum of the negative f and 0. And what that means is you just flip the function f upside down, and then look at where it is positive. Okay, so in this function, for this function, this f minus looks like this: 0, and then this, and then this. So this is the f minus for this function. Okay, and then you can easily see that the f itself is just f plus minus f minus, and the absolute value of f is just f plus plus f minus. Okay. So what I'm trying to say here is that if we define the function f plus f minus in this way, then both of them are measurable, provided that f itself is measurable. The reason is if you check if the f plus is measurable, we just need to check if this set is measurable for any real number t. Okay, so as you can see, if t is less than 0, then this f plus x must be always greater than t, since this is a non-negative value. So that's why this will be just the set E itself. If t is bigger than or equal to 0, then this set here is just you just look at the function f where it is originally greater than t. So that's just this set. But this set is a measurable set since f is measurable. Okay, so this is how we show that f plus is measurable function. And similarly, f minus is also a measurable function. Okay, now let's look at a few examples. Suppose I have a we have a measurable function. Then the absolute value must be measurable as well. And this can be seen easily because if f is measurable, then the f plus f minus are both measurable, and then the sum of the two, which is the absolute value of f, is also measurable. Okay? So if f is measurable, then absolute value of f is also measurable. The converse may not be true in general. For example, if we have a subset of E which is not measurable, it's not measurable set, then we can define f of x to be this. Okay, so this is a characteristic function of a minus 1/2, and then multiply 2 outside. So what this function is actually when the point x is in a, this is the 1. So you get a 1 outside eventually. And if x is not in a, then this is 0, then we get -1. Okay, so that's how this function f looks like. And this function is not measurable, easily show that. But the absolute value of this f is constantly 1. It's constantly 1. So that is a measurable function. So absolute value of this f is measurable, but the f itself is not. Okay. Next example. Suppose we have a function f that defined on R2 to R, and suppose it's measurable in y for every given fixed x. So that means f of x, y. If you fix x, then it will be a function of y, and that is measurable function of y for any fixed x. And also it's a measurable function of x for every fixed y. So you fixed any y, it's a measurable function in x. Then this function is measurable on this R2. Okay, so it's generally measurable. To show this, the idea is that we first construct a sequence of measurable functions, and we show that the sequence will converge to this f. Then using the previous result, we know that if this f is the limit of a sequence of measurable functions, then this f is measurable. Okay, so this is the overall approach. Then how do we define the sequence? For every integer or every natural number k, or every index k, I'm going to define this fk as this. For every given x to y, and if y falls into this open interval, it's j minus k to j minus 1 over k to j over k. So what this actually means is because the function, the y is a real number, let's say this is x, this is the y, then for every k, I can divide this whole vertical line into small segments, right? Say from 0 to 1 over k, half open, half closed. And then from 1 over k to 2 over k, and 2 over k to 3 over k. So we just divide this into small pieces. And also for negative parts, we do the same thing. And each segment has a length of 1 over k. Okay, so we're going to define this function fk of xy that is only that will be constant in each of this band. Say, for example, on this band, I would just say that the function value will everywhere here. The function value will be the corresponding value on the point, on the top line. Okay, so for example, all the numbers on this line will be the same value as this one. Sorry, just this part would be the same value here, and also all the points on this line segment will have the value, same function value as this point, the highest point here. Okay, so that's my definition for fk. Okay, as you can see that when my k goes to infinity, then I have this function fk going to f pointwisely, right? Because for each point, the function value will be eventually getting close, and eventually the limit will be 0. And now let's look at this fk. Just the only thing left is to show that fk is a measurable function. And to show that, let's say that let's just check this set. This is fk xy bigger than t. According to the definition of fk, it's just all the points such that f xj over k is bigger than t, right? But remember that all the points on this line segment have the same function value. So that's why if the point xy makes this bigger than t, then we know that it's just all the points x that is such that it's bigger than t times the length here, times the interval here. Okay, from this point to this point. Okay, so that's actually the set here. But because function f is measurable in y, in x for every fixed y, so I fixed the y here. This function f is measurable in x. That means this is a measurable set, and this is apparently is a measurable set. The product alone is a measurable set, and that is why each fk is a measurable, and also the fk goes to f pointwisely. For k tending to infinity, we know this function f of xy is also measurable. Now let's look at another example. Measurable functions, all the continuous functions are measurable. So this is what this example is trying to say. Suppose we have a measurable set E, then if f is continuous over E, then f is measurable. And the reason is we just need to check if the pre-image of this interval is open, right? If it's measurable. But since f is continuous, so the pre-image of this open set is a open set, and we know open set must be measurable. So that's why this one is a measurable set. Okay, now let's define the the concept of almost everywhere. Okay. So the definition is this. We see that suppose we have a set E. Then we see this. There is a property that holds a property P that holds almost everywhere, or in short we write it as A dot E dot. We write it as A E on or almost everywhere on E if there's a subset of E which has a measure 0, and this property holds everywhere on this E minus A. So that means this is at E, and there's some measure 0 point. So it's just basically you can ignore them, it's just the measure 0. And the P will hold anywhere except over the measure 0 set A. Okay, so this is the definition for almost everywhere. So we can see a few examples. For example, we can say two functions are measurable, are equal almost everywhere, means that the set of points where they are not equal. So this is like the set where these two functions are not equal or do not agree has a measure 0. Okay, so this is if this set has a measure 0, then we say the two functions are equal almost everywhere. Okay, we can also say that the function f is finite almost everywhere on E if the set of points where the function is infinite has a measure 0. Okay, this one, this set is has a measure 0. Okay, finite almost everywhere is kind of different from the bounded almost everywhere. It's different concept because the definition for if f is bounded almost everywhere means that we can actually find a bound. Usually we say this is the function f is bounded by m. Almost everywhere means that there is some m, actually just this m, such that the set of points where the function takes the value bigger than m has a measure 0. Right? This set has a measure 0. Okay, so what this actually compared to the finite anywhere, we can think that a function could eventually go to infinity, even if it's finite almost everywhere, because it's just required that if you look at each point, it is a finite value, except for a measure 0 set. We call it measurable. We call it the finite almost everywhere. But if it's bounded by some number almost everywhere, means that the function value actually falls in between negative m and the positive m, except for a measure 0 set. Okay, so that's the difference between the two. Okay, next we show a theorem that is about two functions being equal almost everywhere. So suppose we have two functions. And they're equal almost everywhere on E. And if one of them is measurable, then the other one is also measurable. Okay, the proof is very simple. So let's say that we can define this set, so I can call this set A. Set A is the subset of E such that the two functions actually agree. Okay, and then because the f and g are equal almost everywhere, we know that the measure of E minus A should be equal to 0. Okay, and now we can see that this function f the function g, we can check the measurability of this set for every given point t, or every given real value t. And as you can see, I can decompose this to two parts. One part is x in A, and the upper part is x is in the A complement. Okay, so I can decompose this into two. And now you can realize that the first set, first set is just equal to this fx bigger than t, because over the set A, the two functions are equal. That's why we have this. And then this second part I don't need to change. I will have another use of it. Okay, and apparently this first set is a measurable set because f is a measurable function. The second one is also a measurable function. The reason is this set here is a subset of E minus A. Okay, and because E minus A has a measure 0, we know this is a measurable set. Okay, so and any set has, and this one will have a outer measure less than equal to the outer measure of this, but it's also equal to the measure of this, since this set is just a measure 0. That means this one also has a outer measure 0, and that means this is a subset. This is also a measurable set. So more formally, I should write it this way. So the mu star of this set is actually less than equal to the mu star of E minus A. But we know that this is just equal to the mu of E minus A since it has a measure 0. So that's why this set here must be measurable. Okay, must be measurable. So that's why both of these two sets are measurable, and the union of them is also measurable. Okay, so now we show that for every t, the set is measurable, so that's why the g is also a measurable function. Okay, so now let's to finish this section, we look at another example. Suppose we have a measurable set E, and it has a positive measure, but it's bounded. Then if we have a function defined over this E, and that is non-zero or is not zero and is finite almost everywhere. So this is true almost everywhere. That means the function, except for a measure 0 set, the function takes a positive finite value. Then for any delta, there exists a subset of E, which we call the E delta. And also there exists a natural number k, such that the E delta has a measure less than delta, smaller than delta. And also this function f is between 1 over k and k for over this set, over the set E minus E delta. Okay, so let's see how to prove this. So the idea is that we can define this set AK to be a subset of the E. So we can say this is the points in E such that the function f is bigger than 1 over k, but it's also less than or equal to k. Okay, for every k, Okay, so now we can also define the z0 to be the points where the function is 0. And we can also define the point, the set where the function takes the value, say f positive infinity. So let's say this function is non-negative, and then we can see that the whole function can be written, or the set E can be decomposed in this way. The E can be written as the union of Z0, Z1, and also the A case. The union of the A case for K from 1 to positive infinity. Okay, and first of all, these three sets do not overlap. Okay, so this kind of a disjoint union of these three sets. But this one here, the AK will overlap. Actually, the AK is non-decreasing, since if we increase K here, then we'll make this smaller and this larger. So that's why this set is potentially larger. So that when K goes larger, this AK will become bigger. So it's a non-decreasing set. It's a non-decreasing sequence of sets, or it's an increasing sequence of sets. Okay. And another thing we know about this is that the function, this measure of this itself is finite. Okay, but it's non-zero. It's finite, and the measure of this and this are both 0 because the function is between 0 and the positive infinity almost everywhere. So that means the measure here, the measure of this are both 0. Okay, and that also means that the measure of this is just equal to the measure of this, and they are both finite. Okay, and now you can see that, as we just mentioned, the mu of E is equal to the mu of E minus Z0, Z1. The reason is just a measure 0 set, and that is equal to the mu of this. Well, we know that this is just equal to the mu of the limit of AK because this AK is increasing, right? And because it's increasing, we know from previous one of the results we learned before is that the limit and the measure can exchange. So that means this is just equal to the limit mu of AK, where K is going to infinity. Okay, so what this tells us is that for K getting larger and larger, this measure will eventually approach to this, or these two are equal. Okay, so that means for any delta positive, we know there exists a capital K such that the measure of mu of E minus the measure of a capital K will become less than delta, right? As we said, this is a increasing sequence of numbers, and they goes to this. And as we said, this is also equal to mu of E minus Z0, Z1. Okay, and now we can define the E delta to be the union of Z0, Z1, and this AK complement. Okay, if we define the E delta in this way, we can see that the measure of E delta is less than equal to the measure of Z0, Z1 plus the measure of AK complement, and then this is just equal to 0 plus this part is just the measure of E minus the measure of AK. Okay, so that is measure less than delta. I should say this is less than delta. Let me rewrite this part. So this is just equal to the measure of Z0, Z1 plus mu E minus mu AK. Right, that's because of this one. And this here is equal to 0. This one is less than delta. That's why the whole thing is less than delta. Okay, and then over the complement of E delta. So the complement of E delta will be just E minus E delta. And E delta is this set here. So it's just E minus the Z0 union Z1 union AK. And then this is just a subset, or it's just a subset of it's just AK, right? It's just AK itself. Just AK. Okay, and now remember what is AK? AK is this set. So that's why the function x function f of x will be bigger than or equal to 1 over k, less than or equal to k for Ox on this Ek, which is equal to E minus E delta. Okay? So that's how we show that there exists such a E delta with a measure less than delta, and outside this E delta, which is just our Ak, we have the function f of x lies between 1 over k and k. Okay, this finishes the proof. Okay, I will talk about several common mistakes that happened in the homework 1. So there are 3 of them. The first one is, although we know that the set of irrational numbers is equivalent to the set of integers, or also the set of natural numbers, but it doesn't mean, it only means that we can list the rational numbers in order. Okay, we can do this one-to-one correspondence between the two sets, but this does not mean that these rational numbers can be ordered in an ascending way or descending way. And as you know that we cannot, although for any two given rational numbers, we can compare which one is larger, which one is smaller, but we don't really have a smallest irrational number. Actually, we don't even have a smallest integer, right? So we only give a one-to-one correspondence, but it doesn't mean that we can actually find a order of those rational numbers. Okay, that's a mistake that happened in some of the homeworks. So that's the only thing that we have. The second thing is, when we talk about the open set and closed set, the relation is that a set E is open if and only if its complement is closed. Okay, but E itself may not be open, may not be closed, or it can be both open and closed. Okay, for example, a set can be both open and closed, such as the set of real numbers. So this set is both open and closed. Okay, and it can be neither open nor closed. For example, this half open, half closed interval is neither open nor closed. So a set could be open, could be closed, could be nothing, and could be both. The only thing that we know is that it's open if and only if it's closed. And actually, yeah, analysis, you know, this open close is, you need to specify what is the whole space or whole set to talk about the open and closed. For example, if we work on the real lines, then this open interval, for example, from A to B, this is the open. But if you consider this open interval in R2, it is not open anymore, right? And in this case, it's called a relatively open. It's only called a relatively open for R1, in R1. Okay. So this is the second problem that appeared in some of the homeworks. The last one is pretty common. So it came from the problem asking you to show that the upper limit of the union of A, K, and BK, the upper limit of this is equal to the upper limit of AK union with upper limit of BK. AK, take the union of this and BK, upper limit of BK. So their common mistake was this. So they say this one, this CK, is the limit, or is the union for K from J to infinity of AK. Okay, so this CK is just this, and the DK similarly is for BK. K from J to infinity. And then someone just write the intersection of such unions, directly as the intersection of each one of them, and then take the union. So this is not right in general. The actual value of the actual result of this one should be this. The union should be taken for all the I and J's, and this is a cross of the. It's a product of the two sums, and then we have cross terms coming out, the Ci and dj. Okay, so for example, I can just take two sets for j from 1 to 2. Just take this as example. Say I have Cj union of Cj dj for j from 1 to 2. And then in this case, it is not equal to the right-hand side like this one. Okay? For example, we can expand this one. The left-hand side is just the C1 union of C1 D1, and take intersection and the C2 D2, union of C2 D2. And then we will really expand this. You'll find that there are 4 terms. The intersection of C1, C2, and then also D1, D2. That's these 2 terms. But there are also some cross terms like C1, D2, and also D1, C2. Right? These are these 2 terms. So it's not just these 2 terms as the right-hand side is, but also additional 2 terms coming out. Okay. To show example why these 2 are not the same, you can take this example below. Say I have this as a C1. Okay, this C2, they do not overlap. And I also have the D1 and also have the D2. These 2 do not overlap either. And then you look at the left-hand side, this one. The intersection of C1, C2 is empty, right? We said the C1, C2 do not overlap. Also D1, sorry, this should be D1. The D1, D2 do not overlap either. Okay, so this is the empty, this is the empty. C2, D1. C2, D1 is this. C2, D1 is also empty. And the C1, D2 is this. C1, D2 is this. Okay, you can see this. Or you can just say that we'll take the union of C1, D1. There will be this area. And the C2, D2 is this and this. So the intersection of them will be this area. So that's for the left-hand side. But you look at the right-hand side, intersection of C1, C2 is empty. The intersection of D1, D2 is also empty, right? Because C1, C2, they do not overlap. These two do not overlap. So this and this, they are both just empty. So take the union is still empty. And this is a counterexample to show that this left-hand side, right-hand side may not be equal. Okay, and this is just for 2, and you have infinite many of them. That's also not true. So a general trick is you can think the union as summation, although it's not exactly as a summation because we're not really taking operations on numbers, but you can think that they behave pretty much like a summation, and the intersection behaves more like the product or multiplication. So imagine that you have a sum of 2 terms times the sum of another 2 terms, and then you should get 4 terms instead of just 2 terms, right? So you have more of them, you can get something similar like that. Okay, so that's a very common mistake happened in homework 1.